Welcome. Let me say something about quivers, multigraphs where also loops are allowed. An example of a multigraph is the Goodwill Hunting graph, where we have here a multiple connection. Finite simple graphs are graphs where we don't have multiple connections and also no loops. Let me remind that every finite simple graph immediately gives a finite abstract simplicity complex obtained by taking the complete subgraphs, the vertex sets of complete subgraphs as sets. I have here an example. As an example, I took the kite graph. One of my favorite graphs is a tripartite graph, K1, 2, 1. And in this case, we have two triangles also. We have a zero Laplacian, a one-form Laplacian, a two-form Laplacian, and we have the corresponding kernels are the Betti numbers. We have a cohomology, and we have Euler-Poincaré tells us that Euler characteristic can be written in two different ways, combinatorially or using algebraically using these Betti numbers. So this is kind of a case of a finite simple graph, right? We have the Kirchhoff Laplacian, which already Kirchhoff looked at 150 years ago. And this is the one-form Laplacian, this is the two-form Laplacian, because there are two triangles. Now, if we have a multigraph with also loops allowed, is sometimes also called a quiver. The notation is not very uniform, so I make clear there can be multiple connections, several connections, not only two, multiple connections, also multiple loops can be allowed. And this is a famous quiver, the Kronecker quiver, which is a category, and the set of all quivers, or the category of all quivers, can actually be seen as a functor category. So it's quite exciting category. And this is a clover graph where we just have one vertex and several loops. This is the magic flower. I call this magic flower, but in general a finite category where you forget about the associativity structure which you have on a category is naturally a quiver. They also appear in representation theory. They have all kind of different attitudes. But for us, this is just a geometric structure which defines delta sets. So I'm excited about this for several reasons. I mean, I'm looking for examples to generate delta sets. And here in this case, we have naturally associated a delta set because we have a Dirac operator. We have a gradient. So here is an example. Actually, I took this the example, just the original example of Euler for the Koenigsberg Bridge problem. Historically, first case where graphs really appeared. I put some orientations which are completely irrelevant. It's like putting a coordinate system in space. It's completely irrelevant for anything interesting you are looking at. For me, it's kind of like a changing coordinates if you change an orientation. But if you give a graph, say in a computer, then you naturally also give an order. So in this case, always I have also given an order. So by giving the simplicity complex, for example, as a set of sets, and I give these sets actually as an ordered list, which is an order, but this is completely irrelevant. For the Kirchhoff Laplacian, it doesn't even matter. For the one-form Laplacian, there it matters, but kind of thinking about the mathematical physicist, this is like choosing a gauge. So it's kind of should be invariant under gauge transformations, and change of orientation is just a gauge transformation. So for us, direction is completely irrelevant, but we use it for writing down the objects like we use a basis when we write down a matrix. So in this case, we have kind of also this zero form Laplacian is the divergence of the gradient, like in calculus, and then the one form Laplacian is the only Laplacian form Laplacian which we have if you look at it as a one-dimensional object. Now, what I was thinking about this week is whether a quiver naturally also defines a higher dimensional delta set. And I try here a couple of examples. You know, if you have, for example, this clover here, there are three loops. You can think about, okay, there's maybe a triangle present because you have three edges, and somehow you can think about this as a triangle. And then you can also, it turns out that you can do that, but your Dirac matrix is kind of not involving this triangle, so it's really a two-dimensional delta set, but the only thing you can naturally do is kind of just not have an interaction between the triangle and the edges, and then everything works also, like in delta sets in general, everything works. You know, you have all the mathematics which you have, McKean-Singer symmetry, and so you have fixed point theorems, you have the Lefschetz fixed point theorem, you have everything which is available once you have a Dirac matrix. So delta sets are really the real thing, but quivers, like graphs, are very intuitive, and especially historically relevant, this Koenigsberg problem, or mathematics, pop culture, the Good Will Hunting graph. So I use this also as kind of a little bit of motivation or examples in a paper which I wrote two years ago, and I revised this a little bit over the week. One of the things is when you submit it and you have to revise it, it slows you down, and but it's such a beautiful result. It's just such a general result of estimating the eigenvalues of a Kirchhoff matrix, of a quiver, and from above and below. This is kind of related to a result which has already been known. In this case, this is appears to be pretty new. It's a very, very general result, and what happens is also I'm excited because the proofs are very simple. It's just essentially just the interlace theorem and induction. And the reason why induction works so well for quivers with loops is if you take a quiver and you take one vertex away, that is then a principal produces a principal submatrix and is again a Kirkhoff matrix of a quiver, which is not the case when you look at graphs. Right? What happens actually when you take that away, you essentially just produce a new, you just add a loop here. You have one vertex less, but you have an additional loop. So this allows induction very nicely, and so the proof is, you know, a few lines. Both estimates can be proven very similarly, and it's also kind of based on the Anderson-Morley estimate, which essentially is in the spirit of McKean-Singer. Actually, Anderson and Morley, they knew McKean and Singer, so they actually got that problem from, I think, McKean or Singer. So, and it's actually very simple. The simple idea is that the one form Laplacian which you have here is essentially spectral to the zero form Laplacian, so the spectral radius is the same. And for that you can estimate the spectral radius using the, you know, the spectral radius is the largest eigenvalue you can estimate by just looking at the sum of the, you know, the largest column sum. The setup of quivers is very natural because of this induction possibility, but it's also interesting because quivers are important in other fields. I mentioned category theory, chemistry. You can model also stronger bonds by multiple connections, and you can take loops and model like this potentials. You can get electromagnetic Laplacians like this. So let me just walk through the three examples which I essentially looked at. So for the Koenigsberg, in the Koenigsberg example, we have interestingly also nice integer eigenvalues 0, 3, 4, 7, and these are the degrees, these are the vertex degrees, which are 3, 3, 3, 5. So this is counting 1, 2, 3, 4, 5. This is counting the vertex degrees. Now the nice thing about this Kirchhoff Laplacian, which you have in the quiver case also, it's also the divergence of the gradient, like for graphs. And so there is there's a exterior derivative, there's gradient, and there is the, so you kind of see it here in this case, you see kind of the 1, 3 edge. So there's 1, 3, 1, 3, 3, 4, 3, 4, 2, 3, the edge 1, 2, and the 2, 4. So I think that should be -1 here. I call this the F matrix because the decays in my paper here, this is usually when you do spectral theory, the decays are the vertex degrees. So the decay looks the same than the exterior derivative, but it's not. It has nothing to do with the exterior derivative, of course. The decay are just the ordered, sorted vertex degrees. In this case, that works beautifully, and you can look at random quivers and see how good these estimates are. I think the lower bound one should be able to improve this a lot. I think also for larger graphs, the upper bound can be improved by a constant times decay, maybe 1.5 times decay or so, but I don't know. So, but in general, these are sharp estimates in general. The second example which I looked at is clover, ordinary clover, not like the lucky clover here with 4 leaves, the usual clover. In that case, you know, theorem 1 is also sharp. You can write down everything. And I was wondering in this example about the, you know, a triangle structure. You can add it, but as I said, it doesn't interact with the, you know, with the edges, and so. Yeah, so it's a 2-dimensional delta set, but not so, you know, different than the 1-dimensional skeleton. Also here, in this case, it's the same situation. I tried, you know, if you try to put here 1, 1, 1, because you think about the triangle consisting of these 3 edges interacting with each of the edge, but it just doesn't work. If you write this down as a Dirac matrix, this is just to check whether it's a delta set. You take the Dirac matrix, or this matrix, you write it down. You should be a block diagonal matrix, which means, you know, that the axiom system of the delta set is valid. And so in this case, that works. But again, the triangle does not interact with the rest. Here I look at the Goodwill Hunting graph, which also kind of, you know, traditionally, like in the original problem, which on the MIT board was kind of written down to write down this matrix here, this Kirkhoff matrix. And so this is the Kirkhoff matrix, and then there is a one-form matrix, which is also essentially isospectral. So again, if you look at just L0 and L1, then you have just a 1-dimensional delta set. And the question is, can you do a 2-dimensional delta set, which is interesting? And yes, in this case, you have really an additional triangle. And when you look at this additional triangle, then the Dirac matrix really gets a little bit larger, right? We have now 10 objects, we have 4 vertices, we have 5 edges, and we have 1 triangle. 10, this is 10 times 10 matrix, this is the 1 form. And then we have a 2-form Laplacian, which is a 1 times 1 matrix. So there is already light, there's already electromagnetism on this simple graph, and so this gives hope that you actually can, you know, maybe push in general also in a canonical way attach a higher dimensional delta set to a quiver. And the question is then, you know, what do you count as triangles, what do you count as tetrahedra, what do you count as higher dimensional cells? And so in this case, it really works. In this case, with the triangle, then we have an Euler characteristic 0. It's essentially just a, you know, homotopic as a delta set to the circle, right? This loop with two connections is essentially a circle. While we have here, in this case, this is actually -1, the Euler characteristic -1. Think about this as a, you know, figure 8 graph. Also this you can think about as a figure 8 graph if you just look at the 1-dimensional simplistic complex. You don't look at the meat, the really interesting meat, which is the triangle. You just cut away the meat and you have only the skeleton. That's why it's called the skeleton. So for some reason, the mid of the 20th century graph theorists have decided to look at graphs as 1-dimensional simplistic complex, which of course is a loss because you lose a lot of interesting structure. Well, that's what I wanted to say today.